Good morning, everyone. Welcome to our lecture, Physical Chemistry 4 on the electronic structure. Yesterday, I had to rush out a little bit, so I'd like to continue where we started, but I need to apologize. Yesterday's lecture was not recorded in its entirety. Only half of the second half of it was actually recorded. I still have to post that online. So the first part where we still discuss the examples was not recorded. So I hope you took notes and paid attention. And this is being recorded already, so for today we should be good. So we discussed the variational principle, and let me scroll back here. The idea is shown here in this graphic. So this is very fundamental picture, right? Which you should have in your mind. It's this picture should come to your mind when talking about the variational method. Yeah. So basically, it's about knowing that your E tilde, which we now also call W, is identical in the coefficient space that spans your wave function, right? That affects your wave function. So if you wish, these are trial wave functions, that this is some function. And if you have some initial trial wave function, see, say phi initial, right? The variational principle allows us, by imposing that the gradient be 0, to identify a phi optimum. And we know that the corresponding energy must be above the true energy Okay, so that's how close how you can get. Typically, you don't hit exactly that target because the functions we typically choose are not complete, and they are not. It's not a complete set of eigenfunctions. Right? You remember from the theorems. If we had that, then you could get the exact answer from the variational principle. Now, we discussed the principle, we discussed some examples, and we then in the second part of yesterday's lecture, we entered the more generalized procedure to arrive at the solution. And this procedure can be seen as an algorithm, right? So this is something you can program, okay? We can make use of computers. Now, why would we want to make use of computers, you might ask? Now, if you are up to date, right, this should be, the answer should be obvious, right? Computers are everywhere. Furthermore, there's something known as Moore's law, which states that the computer, the transistor density doubles every 2 or so years, meaning that computers' power grows exponentially. Now, Moore's law has been formulated in a sort of an unfortunate way. Ray Kurzweil gave a much more compelling definition, in my opinion, which states that the compute compute tasks, they become cheaper every year, okay, by a fixed percentage. So in terms of dollars or Swiss francs, this means that as time progresses, you can compute exponentially more for the same amount of money, right? So the value of compute decreases exponentially. Now, this is, in my opinion, a more general and more powerful law. And if you want to look more, to hear more about this, you should Google Ray Kurzweil. He is a very well-known scientist and philosopher and in computer sciences, and artificial intelligence research. He does many things. I'd strongly recommend to look up his contributions on the role of computing and so on. Now, this means that as time progresses, we can solve exponentially more difficult problems. And I do believe that this is a very strong case for theory, right? I will challenge you to identify, name one experiment which, as time progresses, becomes exponentially cheaper. This is not an easy thing to accomplish, and so very few examples exist. One of them is, for instance, gene sequencing. You have had similar progress in gene sequencing. I still remember when it used to cost millions of dollars to sequence a single genome. By now, it's really a small fraction of that. Similar with computing, and this means we can solve increasingly larger variational problems. Okay, so to increasingly better degree of accuracy. So if you are interested in being in the future on the right side of things, if you wish, I would recommend to consider computational chemistry for that. All right, so this was a little advertisement for my field, but now let's continue with the particular discussion where we are at. We had made this ansatz, just to recall, of a bunch of basis functions, which we did not specify any. We didn't go into detail. We just presume you know this known, and this is unknown, must to be determined, right? That's the job. Right. And we have n, k equals 1 to n of such terms. Now, by doing this ansatz and introducing this into the definition of our matrix elements, so we put this into our phi. This is our phi. This goes into our matrix elements, right? This we call Hij. Is Ij, right? And by virtue of the variational theorem, we arrived at a matrix which runs from 1 to k to n, 1 to I to n, which we call this AIK matrix, right? And we have seen that there's some coefficients, right? Ci, and that this whole thing must be 0, right? So you have these two indices, right? K and I. And then I told you about this trick that the determinant of the matrix has to be 0 for this equation to be meaningful, right? Meaning to have non-trivial solutions for C. So this one then and only then things are meaningful. All right. So this means we have a separate, an additional equation of the entire A matrix, okay? Now this determinant, as you know, a determinant can be written as a polynomial, right? And if this polynomial must be equal to 0, then you can search for the roots of this polynomial, right? And so the degree of the polynomial corresponds to the size of your matrix, right? So if you have an n by n matrix, the degree of your of the polynomial coming from your determinant is going to be n, right? So in other words, there are n roots. Now this equation we call the secular equation, right? Or characteristic polynomial. There are n roots for this, and we can use them to solve for our energy W. And now we do this n times. So we have a set of W's. And this is exactly what you would expect from solving wave equations, that there are multiple solutions. Just think of particle in the box, quantum harmonic oscillator, hydrogen atom. You have many different states, right? So for each state, you get a solution. You get the entire spectrum of energy values, right? So the meaning of this is obvious, right? Here's your energy, and here are your different W's, W1, W2, up to Wj, up to Wn. And then once you reach Wn, you reach the finiteness, right? N Remember, n is the number of basis functions you're using. So you have hit the limit of your number of functions which are at your disposal. You can't go further, right? Now, if your set of functions f is complete, right, then you have covered the complete quantum spectrum of your system. In practice, it's rarely complete. It's very, very special to be able to construct complete sets of functions. If you're mathematically inclined and you devise a method to generate complete sets of functions, of eigenfunctions too, for instance, the Hamiltonian, it's pretty sure you're going to get a call from Stockholm next year. So there's no proof that it's impossible to devise this, right? That's what I'm trying to say here. So it's part of the academic education to also point out such open challenges or open frontiers, right? Open questions that typically they are not being discussed much in the literature and textbooks. Now, what you have now, hence, is something where for every W, you get this box, right? So you can use this W to insert it in this equation here. And then the entire AIK matrix is known. And hence you can solve for your coefficients. Okay. But this means, of course, that you will have coefficients for each wave function. Right? So you really have to be able to count up to 3 in this course. Right? There's a coefficient, an index k, which is in your series, in your basis set expansion. Then there is the index I, which you generated by differentiating with respect to coefficient I, Ci, right? That's where it comes from. These two guys span that matrix n by n. But then you have a third dimension, which is your state, right? So that's the J, right? So in other words, your matrix now depends A, I, J, K, right? And you multiply it with coefficients I, J, right? And this generates your, this corresponds to your wave function J, right? C, I, J, F, I. Okay. So this is the wave function for your state J. The energy is, of course, what you've used in your matrix to get there. So what you see here is what's working under the hood, right? Is this? If this is your k dimension, right? And then this is your I dimension. Now let me excuse me. Let me pick the other index. It doesn't matter which index you pick. CKJ, and here we use K above, right? So I'd like to stick to that. Yes. So the K dimension is your basis set expansion. or your series expansion, right? The I dimension is from differentiating to Ci, and the J dimension is from solving the secular equation. Finding roots of secular equation, right? So that's what we mean. Right, so we have n roots of those. We have n times the roots. We differentiate it n times, and in the series you have n terms. Okay. So you have an n times n space. So that's what you have to live in. That's the world of the electrons of your system. All right. Now let me make some remarks here. So if you listen carefully, these remarks will be obvious, but it might help to repeat and reiterate, to memorize things. So, and if you were not aware of them, then this is the time when you should really try to penetrate the content of these remarks to fully grasp what's going on. So your set of energies it depends, Jay, it depends on your set of basis functions. Right? The C's, right, the coefficients, they will be optimized anyways, right? So the true dependency is in your basis sets, right? So if I change my basis sets, the entire spectrum of my energies is going to move. All right. So you see this not on coefficients CKJ. This becomes very much obvious since your W results from setting your determinant of the matrix equals 0, and in this matrix there are no coefficients. Right? So you really need these coefficients only for the wave function. Right? For calculating the energy spectrum, your basis function space is good enough. B, what we just discussed, it all corresponds to a linear variational Ansatz in basis of n linearly independent basis functions. So for all j, right, one has to solve n equations 1 to I to n with n unknown c i's, right? I coefficients. So this is remarks and summary, if you wish. Setting the n by n secular determinant equals 0 yields n energy values Wj with best representing, which represent the best approximation to true to corresponding true energies. A, B, C, D. Substituting back the W system of equations yields sets of coefficients. Okay. So C, what did we say? Kj, right? And so you have this for every level. So it's going to be n times n, those guys, which determine the wave functions by j for all states j. Okay, so generally there are two jobs to be done. First, you need to calculate the energy, and then you need to calculate the coefficients for each energy state. And in this lecture series, we will do this, okay? You will learn how to do this. And most importantly, for the Huckel theory, where it's so easy, you can, in many cases, do this by hand, okay? You don't even need a computer for that. Now, in general, you want to use a computer because it becomes too cumbersome, but the principle is the important part, right? So before you learn how to program things, you first need to fully understand the theory behind things. Now, let me finally mention the larger n is the same as saying the more basis functions we use, the closer Wj to true values Pj. Okay. So for the complete set of functions, you should find the exact solution, the true solution. Now, I'd like to, are there questions so far? Is this clear to everyone? So let's continue with the next subsection, which is sort of reiterating on this. This is sort of rather technical, right? So it's not so deep scientifically or conceptually, but it can prove helpful in practice. And so this is subsection 3.3, which is doing the whole thing in matrix notation. So we already started this a little bit, so you got a head start. But basically what we have is a sum over your basis set coefficients, right? And I drop the n now, it's implicit, right? K runs from 1 to n, just as all the other indices. And then we have our coefficient k, then the matrix ik minus s minus w s ik. This sum has to be 0. And so this is for all I equals 1 to till n, right? Now, so this is the matrix we had before, and we can write this slightly differently, right? Rather than just calling this our A ik, we can also write this in such a way where we have a big matrix which consists, each element consists of a difference right? And this gets to be multiplied with the vector c. Okay. Now, matrices, sums or differences of matrices are just matrices again, right? If they have the same number of elements. So that you can totally write your A matrix in this way, right? And the W is just a number, so you can put it in front of the matrix, right? So that's what you have here, right? And then the secular determinant just means H minus omega S equals 0. Okay. So if you look at this, right, these two equations basically summarize the entire chapter. Yeah. All the handwriting we did so far, it's summarized in this way, right? And that's, of course, a very appealing way. Now, you can write this also in this element-wise fashion, where you say, okay, where you write something like this, and then you note to each root, right, there is a solution vector. To each root j, there's a solution vector Cj. Right? So in other words, we have that's it, right? The set, the n equations like this have solved your entire quantum problem. All right, now we'd like to make this even more pretty, but we can only do this using an assumption, which is not always a given, but which we would like to do, of course, by thinking of chapter 2. And this assumption is that our basis functions are not only known to us, right, but also that they behave as we would like them to behave. Now, let's put it like this. If we assume, now there's this joke, right? It's maybe inappropriate, but yeah, you know what assume stands for, right? You make an as out of you and me, right? So, but so the assumption is basis functions Moss doesn't find this joke funny, so I think he's heard it too many times. Basis functions f are orthonormal. Orthonormal means orthogonal and normalized, okay? All right. So this means our entire integral is Ij. Yeah, this integral is the Kronecker delta, right? This integral is d tau fi fj is Kronecker delta Ij. And so what happens then to our nice set of equation. Let me write it like this. Sum over k ck hik minus omega sik is hence ck hik minus omega. And actually now I put the bracket here in front, omega wck delta ik. Okay. I'm summing over this, and this whole thing still must be 0, right? So we have this for all the i's, and so what you can see now is that basically your matrix equation, right, your set of equations with the coefficients, which has to be 0, we now partition this into 2 matrices, right? We factored out the C vector. And so this difference between these 2 matrices must be 0. So I can pull one over to the other side. And so this means that in this case, right, only k equals I survives, right? So this is a constant omega ci, right? So the Kronecker delta kills this, and our sum on the left survives, and we have ck hik equals ciw. And of course, still is set for all the i's, right? So that's the same as writing H11 C1 plus H12 C2 and so on until H1n Cn equals C1 W. And then the same here, H21 C1 plus H22 C2 plus H2n Cn equals C2 W. And now we go down further, Hn1 C1 plus Hn2 C2 plus Hn Cnw. Okay, now we can factor out again the vectors, right? And then you see that this is your H matrix times a C vector, and this must be equal to your W times a C vector. So the H matrix, this is the same as saying H11, H12, H1n, HNN, HN1, HN2, right? C1, Cn. You see this? All right. Now, again, this is just for one W, right? So you would get this equation. So I can put in a J here and say for all J, for all states. But this equation is a funny equation, right? What you see here is something operates on your coefficients, which represent the state, right? And what you get then on the other side are your coefficients again with a number in front of it. And that, of course, is nothing else than an eigenvalue equation. Excuse me, I should put the J here as well. If I put the J there, or let me keep this implicit here. And say we do this for all states. So for any state, we have this eigenvalue equation, and this is nothing else. Right? The C's correspond to your wave function. Is nothing else than the discretized Schrödinger equation. Right? If you solve this equation for your coefficients, you've solved the variational problem, you've solved the Schrödinger equation. Right? That's how it all comes together, okay? It's not in a discretized version, that's how you can solve Schrödinger's equation, right? It's equivalent. It's the same thing. And so far in quantum mechanics, you usually guess some ansatz for your differential equation and for the operators in the Schrödinger equation, for your Hamiltonian. Here, you simply have to solve this linear algebra problem given a Hamiltonian matrix, right? This is also what we call the Hamiltonian matrix. Right. Any element is, of course, your basis function I with the Hamiltonian. I don't know what's happening here. Okay. So if these eigenfunctions are, if these basis functions are the eigenfunctions of the Hamiltonian, which would satisfy this orthonormality condition, then we can simply write it in this discretized version. Now it's 10 o'clock. I'm not entirely done yet, but I have to call it a day now. We will finish this chapter on the variational principle. We will need 1 more hour or so, but it didn't fit in today. Now, next week, unfortunately, I will not be able to give the course, and instead my postdoc, Guido von Rudolph, will step in, and he will teach the chapter on perturbation theory. Right? So within our joint research, we use perturbation theory quite a lot. And so he's become an expert in this. So I hope you will enjoy that little excursion. And I will get to see you again in the subsequent week again. Are there any questions at this point in time? If not, I'd like to thank you very much for your attention. And I still wish you a good day and a good rest of the week.
Bye.